Hi everybody, I'm back. So we're now in video 4, I believe, and we're going to continue talking about substitution with different types of nucleophiles. And more specifically, we're going to be using electrophiles which are related to epoxides. And so in the previous video we talked about the alkylation of these species under basic conditions. The other mode of alkylation winds up being under acidic conditions. And so generally speaking, what this type of reaction looks like is you've got your epoxide, and you are going to treat this with some sort of acid plus some sort of nucleophile. And generally speaking, what this is going to wind up looking like is you're going to crack open your ring, similar to as before, generating your alcohol and your carbon-carbon bond that's 2 carbons away. And so generally speaking, when we're dealing with this type of reaction, our nucleophile is often the solvent. So and typically these types of nucleophiles are not very strong. And so an example would be running this reaction in ethanol, and ethanol is the species that winds up cracking open your ring. H plus can pretty much be whatever you would really like that to be in terms of an acid, as long as it's a relatively strong acid. So an example of this type of reaction you can think of as adding some sort of methanol. And so I'll say in this case that we are going to add, in terms of our reactions, some sort of acid. So we'll use sulfuric acid here, for no other reason than it's nice. And so we'll then use methanol as both our solvent and our nucleophile. What this will allow us to do is to create a new carbon-oxygen bond as well as crack open our 3-membered epoxide ring, giving us the alcohol here. The mechanism for this transformation is slightly different than we've seen under the basic and neutral conditions, but the general scheme of this SN2 backside attack winds up being the same. So let's switch the camera, and I will keep on going. Okay, let's talk mechanism. And so the way in which this is going to work is you've got your epoxide, and we are going to be treating this with a solution of acid, so H2SO4 in methanol. And so the first thing we want to think about is what happens when we add a really strong acid to a polar product solvent like methanol, water. What we wind up having happen is dissociation of that acid. So specifically, what this will wind up looking like is this. We've got our sulfuric acid here. And this sulfuric acid is going to do a pretty good job of protonating our methanol. I realize now that there's not a chance you guys can see this, so let's move this over here. No worries. It's just Chris in the video. Say hi, Chris. Hi. Snow day lectures. Okay, so sulfuric acid looks like this. We're going to protonate our methanol. From the sulfuric acid, and that will give us our oxonium ion here, so H2OCH3 plus, so the oxonium bisulfate, and so O minus OH. And so it's actually this species that's likely going to be our most acidic species in solution. In the same way that if you drop a strong acid into water, H3O plus winds up being your strongest acid in solution. So getting back to where we are on this cracking open of the epoxide here, what we're able to do then is we're able to take an equivalent of this protonated methanol, and we're able to use the lone pair of electrons on our epoxide to pull off that proton. Okay? And what this will wind up giving us is this will wind up giving us our protonated epoxide. at this point, we've turned what is sort of an leaving group, even though it does have that spring-loaded ability to relieve that ring strain. Carbon-oxygen bond with an O- as a leaving group is still not great. But now we've converted that leaving group to something with an OH+ as this species here. And remember, by protonation of something like an alcohol, we can turn a really terrible leaving group into something that's really good. In previous cases, water, this winds up being an alcohol here. And so we've now really supercharged this electrophile so that a poorer nucleophile is able to come in and open this ring. So in this case, methanol will come in, crack open this 3-membered ring, giving us our opened alcohol species and our protonated ether product here. So there's a positive charge here. So what we need to do then is we need to go ahead and remove that proton so that we have our neutral product. Generally speaking, again, we want to look for the most basic species in solution. So you have the option of bisulfate, you have the option of methanol. Generally speaking, your solvent is going to be more basic than the conjugate base of a strong acid. Because remember, conjugate bases of a strong acid by definition are pretty weak. And so I'm going to go ahead and use another equivalent of methanol here. To go ahead and pull off this proton, giving us our deprotonated ether product. Plus an equivalent of protonated methanol. And so the cool thing about this is that when dealing with these acidic type acidic type epoxide openings, this acid is actually catalytic. And what that means is that while we use an equivalent of this to make the reaction happen, we spit out an equivalent of this in the end. So this product is not used up. So in our first step here, we wind up giving a proton from protonated methanol to protonate our epoxide ring and turn that into a good electrophile. In the end, after our nucleophilic attack happens, we wind up having an extra proton that we have to remove. And so methanol is able to come back in, pull off that proton, and regenerate our acid catalyst while giving us our product. And so remember, catalysts are neither used up or created nor destroyed really in these types of reactions. That's not always true, so some reactions do create their own catalysts. They're called autocatalytic reactions, but we're not going to worry a whole lot about them today. Where we're going in the next video is, like in the previous video, we're going to look at the regiochemistry of addition under acidic conditions, and additionally some of the different types of products you can make with epoxide opening under acidic conditions. Hope to see you soon.